Hello, this is Dr. Brown. In this video, we're going to cover and review the topics that you'll be seeing in test 3. So this is a practice test that's up on the website, and we're going to start working some problems. The first problem is to find the location of the indicated absolute extremum for the function. This would be the absolute max or the absolute min. And they're asking for the absolute maximum. And really, all you need to do is look at this graph and see that the absolute maximum occurs at x equal -1, and the value is 4. So the answer is D. Here we want to find the absolute extremum for this function over the interval 0.5 to 3. So what you need to do is write down the function. And I'm going to rewrite it because we're going to take the derivative minus x to the -2. And we need to find a critical point if there is one. Critical point is when the derivative is not defined or where it is 0. Well, the first derivative of this function is 2x to the -3, which is equal to 2 over x cubed. We set it equal to 0. And we notice that in no way can this function ever be 0. And so there is no critical point. So the next thing to do is to check the endpoints. So we're going to check the first endpoint, f at 0.5, is equal to -1 over 1/2 squared, which is equal to -4. And then we'll check the other endpoint, f of 3, is equal to -1 over 3 squared, is equal to -1/9. And this is the min, and this is the max. And so the answer is C. Minimum is -4 at x equal 1/2. The maximum is -1/9 at x equal 3. And the next problem is a little bit more involved, although it's fairly simple. The function we have is a piecewise defined function. Both pieces are quadratics, except they're different quadratics. And they're defined up to +1 and past x equal +1. We're asked what are the critical points or domain endpoints where f prime is undefined, is the first question. And what you need to do is to graph this function. And I have already graphed it and have shown various views of the graph here. You put this in for f1 or y1, and put this in for f2 or y2. And if you go to the standard window, after you graph it, you'll see this. And you can see we have two parabolas. This one actually goes up like this and comes down, and the other parabola is here. And you can quickly see that the composite function, let me pick another color, the composite function, we'll do this in red, for x less than or equal to 1, it is the red. And then at x equal 1, the other parabola takes over. And so we have something that sort of looks like this. And this occurs at x equal 1. Now I have changed the window. I've changed the window here. And so you can see both parabolas. And here I've even zoomed in and then zoomed in even more, or actually about the same. But we're calculating the values of y for x equal 1. For the first function, it's minus 2. For the second function, it's minus 2 at x equal 1. And so we know that this function is continuous. In other words, there's no gaps. The only thing is that at x equal 1, the derivative is not defined, because you can see coming from the left, the tangent line might look like this. Coming from the right, the tangent line might look like this. And since one is negative slope, the other is positive slope, they won't agree at x equal 1. So f prime is undefined at x equal 1. Now you could have figured all this out by just putting this in, and I still would zoom in a little bit. Now we're asked where are the critical points where f prime is 0. Okay, so now we're going to look at the function. First, we're going to look over here, and we're going to look at y is equal to minus x squared minus 9x plus 8. And we want to calculate the first derivative. It's minus 2x minus 9. And we set it equal to 0. And it's 0 at x equal minus 9 halves. The second area is over here on the right. And let me go ahead and highlight this again in red. And then for the second parabola. We just discovered that at x equal minus 9 halves is where the derivative is 0 for the first, for the left side. For the second area, we look at y equal minus x squared plus 3x minus 4. Take the first derivative, and it is equal to minus 2x plus 3. We set it equal to 0, and that is 0 at x equal 3 halves. So looking over here on the right at x equal 3/2, you can see the derivative is 0. We would have a horizontal tangent line. So critical points are x equal minus 9/2 for the first one and 3/2 for the second one. And the second part is asking us the points corresponding to the local maxima. Here we just have to look at x equal minus 9/2 and calculate f of minus 9/2. We'd be using the first quadratic, and that's equal to minus 9/2 squared. Plus 9 or minus 9 minus 9 times minus 9/2 plus 8. And you'll see that this is minus 81 fourths plus 81 halves plus 8. And if you add all that up, you get 113 fourths. So the first point is at minus 9/2 and 113 fourths. The second point is at x equal 3/2. So we calculate f at 3/2 using the right quadratic, and we get minus 3/2 squared plus 3 times 3/2 minus 4. And if you add all that up, you get minus 7/4. So the second point is 3/2 and minus 7/4 is the other maximum. And actually, that is the entire problem. Number 4, we want to find the value of values of C that satisfy the equation f of B minus f of A divided by B minus A equal f prime of C. And what we're looking for is if we have a function of x starts from A to B and is continuous and differentiable between those points, we would be looking to find out if we drew a straight line between point A and point B, it has a certain slope. What points in between have a derivative that's equal to the slope of the red line here? And you can see in this particular case, I could imagine one here and one here. Of course, I just drew not this problem, but another function. Now we're going to work the actual problem. First of all, the problem is a quadratic on the interval minus 2 to 1. A is equal to minus 2. B is equal to 1. F of 1 is equal to 4 plus 4 minus 3 equal 5. Alpha minus 2 is equal to 4 times 4 minus 8 minus 3 equal 5. It just so happens in this case, alpha B and alpha A are equal to one another. So now we can calculate F of 1 minus alpha minus 2 over 1 minus 2 is equal to 5 minus 5 over 3. And it equals 0. So now we have to answer the question, is there a point between these 2 points where the derivative of f of x, which is 8x plus 4 equals 0, and that point would be x equal minus 4 over 8 equal minus a half. And that point is certainly in between minus 2 and 1. So the answer here is minus 1/2. Now, here's another function. We want to answer the same question. Here, the interval is 1/18 to 18, and the function is 9x plus 9 over x. Here we have b equals 18, and a is equal to 1/18. And so alpha of b equals 9 times 18 plus 9 over 18. Alpha of A is equal to 9/18 plus 9 over x, which is 1 over 18. And this equals 9/18 plus 9 times 18. And here we have it again. Notice alpha b minus alpha of a over b minus a is going to be 0 because these two values, alpha b and alpha of a, are the same, divided by 18 minus 1 over 18. No matter what the denominator is, this is 0. So now we look at the function f of x, rewrite it so you can take a derivative. 9x plus 9x to the minus 1. Take the derivative, which is equal to 9 minus 9x to the minus 2 equal 9 minus 9 over x squared equals 0. And so we get 9 over x squared equal 9. Cross multiply, we get 9x squared equal 9. X squared equal 1. x equal plus or minus 1, but you can only pick the one that's over within the interval, and that would be x equal 1 is the answer. So the answer is C equal 1. Now let's look at this function. It's a cubic. We want to find the function's local and absolute extreme values, if any, saying where they occur. Okay, the function f of x you take the derivative, it is equal to minus 3x squared minus 18x minus 24. And we set it to 0. So let's factor a minus 3 out of this. Get minus 3 times x squared plus 6x plus 8 equal minus 3. We can factor this into x plus 2, x plus 4 equals 0. So x equal minus 2 and x equal minus 4. Now notice there are no endpoints. This is defined from minus infinity to plus infinity. So what we might be looking at are some local minimum or local max. So the best thing to do here is, since it's easy to calculate the second derivative, is to find out whether the function is concave up or concave down at these 2 points. So the second derivative of this function is minus 6x minus 18. Now let's test minus 2. Second derivative of minus 2 is equal to minus 6 times minus 2 minus 18 equals minus 6. That means it's concave down if it's negative, which means it looks like that. And that means it's a local max. Second derivative for minus 4 is minus 6 times minus 4 minus 18 is equal to 6. It's positive, so it's concave up. Looks like that. So this is a local minimum. And so the answer here is C. Local max at x equal minus 2, local minimum at x equal minus 4. Here we have a function. We want to find the largest open interval where the function is changing as required. And here they're asking what's the largest open interval where the function is increasing. Well, the first derivative tells you whether it's increasing or decreasing. So we need to take the first derivative. Notice we're going to have to use a chain rule here. We have y equal x squared minus 9 squared. And the first derivative is going to be 2 times x squared minus 9 to the first power But since what's in parentheses is not just plain old x, we have to use a chain rule and take the derivative of x squared minus 9, which is 2x. And this is equal to 2 times x minus 3 times x plus 3. And I'll just put the 2x here. That's equal to 0. Obviously, it's 0 if the factors are equal to 0. So the points are x equals 0, x equal minus 3, and x equal plus 3. So the next thing to do is to divide the number line into several segments from minus infinity x between minus infinity and minus 3, x between minus 3 and 0, x between 0 and 3, and x between 3 and plus infinity. And we need to pick test points that I call TP, test points. And we pick a point in this interval, and the easiest is minus 4. For the next interval would be minus 1. For the next interval would be plus 1, and it would be plus 4 here. So we calculate y prime at minus 4, and we get, let's write down the derivative. Here's your derivative, which is 4x times x minus 3 times x plus 3. Plug into that, plug in minus 4, and we get minus 16, minus 7, minus 1. It's less than 0, so we know that it's decreasing. Now we'll plug in minus 1, and we get minus 4, and 2, which is more than 0, so it's increasing. And now plug in 1 into the derivative, and we get 4 times minus 2 times 4, less than 0, so it's decreasing. And then finally plug in 4, and we get 16 times 1 times 7 is more than 0, so it's increasing. So we want to find the largest open interval where it's increasing. It's increasing here, and it's increasing here. Now this interval is from minus 3 to 0, which is the interval of 3. This interval is from 3 out to infinity, which is be the largest. So the answer is 3 to infinity. Now we have a problem. We want to find the absolute maximum and minimum values of this function, which is ln of sine of x between pi over 6 and 2 pi over 3. So we need to check the endpoints and any points where the derivative is 0. So f of x equals ln of sine of x. Here again, we need the chain rule. F prime of x the derivative of ln of x is 1 over x. So the derivative ln of sine of x is going to be 1 over sine of x. But we have to multiply by the derivative of sine of x, which is cosine of x. And we want to set this to 0. That is only 0 if cosine of x equals 0. And if you look at your unit circle or look at the graph of the cosine between these 2 points, x is equal to pi over 2. It's also 0 for x equals 3 pi over 2, but that is outside the interval pi over 6 to 2 pi over 3. So one point we're going to check is there. So let's calculate alpha pi over 2 is equal ln of sine of pi over 2 equal ln of 1, which equals 0. Elf at the first endpoint is alpha pi over 6 is equal to ln of sine of pi over 6 is equal to ln of 1/2, and which is equal to minus ln of 2. And if you calculate that, it's minus 0.693. Now we'll calculate elf at 2 pi over 3. The other endpoint is going to be ln of sine of 2 pi over 3. Looking at your unit circle, the sine of 2 pi over 3 is the square root of 3 over 2. You calculate this and you get minus 0.143. So look at all 3 of these values. Zero is the max, and the value at pi over 6 is the lowest value of the min. So the answer, the maximum, is 0 at pi over 2, and it's equal to minus ln of 2 at pi over 6. Here we're going to look at a graph over the interval minus 6 to 6 and identify the open intervals in which the function is increasing and decreasing, and identify the function's local and absolute extremes, if any, saying where they occur. Now, the function is going to have a relative, actually it's going to have the absolute min at x equal minus 2, and at x equal plus 2, it's going to have a max. And it's increasing between minus 2 and plus 2. And decreasing from minus 6 to minus 2, and also between 2 and 6. So looking at the various possibilities, the answer is B, increasing -2 plus 2, decreasing -6 to -2, and 2 to 6. By the way, that doesn't look like a 2 down there. It's a 2 to 6. So the answer is B. Another problem, we want to locate the local extrema and identify the intervals where the function is concave up and concave down. Well, first of all, I'm going to highlight this concave down, and maybe to use another color, it's concave up. So now looking at the local max, is going to be here, which is -3 and 3. Local min is here, 3 and -9. And concave down from -infinity to 0, concave up between 0 and infinity. And that answer is answer C. Number 11, we want to use L'Hopital's rule to find the limit as of this function as t approaches -5. First of all, you need to see if you can use L'Hopital's rule. Let's plug in -5, and we get -5 cubed -6 times -5 plus 95 divided by -5 squared minus -5 minus 30. And if you add all this up, you get 0 over 0. And this satisfies the requirement of L'Hopital's rule that the numerator is approaching 0, the denominator is approaching 0. Therefore, you can take the derivative of the numerator and denominator. So we're going to take that this is going to equal the limit as t approaches -5 of the derivative of the top, or numerator, which is 3t squared, -6 over derivative of the denominator, which is 2t, -1. And plugging in -5, we get 3 times 25 -6 over -10 -1. And this equals 69 over -11. So we got -69 elevenths. is the answer. That's the limit. Here again, we want to use L'Hopital's rule to find this limit. You probably recall that on the first test, you would work something like this by multiplying the numerator and denominator by the conjugate. In fact, here's how you would have done it. You would have multiplied the top by the square root of y plus 25 plus 5, and then see if you could find the limit. In this case, if you plug in y equals 0, you get the square root of 25 minus 5 over 0, which is equal to 0 over 0. So we can use L'Hopital's rule. So this limit is going to equal the limit as y approaches 0 of the derivative of the numerator, which is, let's just do the derivative of the numerator. We have y plus 25 to the 1/2 power minus 5. This derivative of this would be 1/2 y plus 25 to the minus 1/2 minus 0. So this is 1 over 2 square root of y plus 25. So the numerator is 1 over 2 square root of y plus 25 divided by the derivative of the denominator, which is 1. And now plug in 0. And you get 1 over 2 times the square root of 25, which is 5. So you get 1/10. So the answer is 1/10. The last one on L'Hopital's rule is to find the limit. And notice here that as t approaches infinity, the numerator is going to infinity and the denominator is going to infinity. E to the t overpowers minus t greatly, so both the numerator and denominator are headed for infinity. So that limit now is going to be equal to the limit as t approaches infinity of the derivative of the numerator, which is e to the t plus 2t. The derivative of the denominator is 2e to the t minus 1. This is still infinity over infinity. So we take another derivative. We can keep on doing this. We take another derivative and we get e to the t plus 2 over 2e to the t. Now, we still are getting infinity over infinity, but notice, let's take the derivative again, and you get e to the t over 2e to the t. Notice e to the t's cancel, and you get that the limit is 1/2. Number 14, we want to find the number of units that must be produced and sold in order to yield the maximum profit given the equations for revenue and cost. Well, the profit, P of X, is equal to R of X minus C of X. And we want to take the derivative of the profit after we calculate it. The profit is equal to the revenue, which is 30x, minus 0.5x squared, minus the cost, which is 2x plus 6. And this is equal to 28x minus 0.5x squared minus 6. Now take the derivative of the profit and set it to 0 to see if we got a point which will maximize or minimize it. And we get 28 minus x equals 0. So x equals 28. It's the number of units that will maximize the profit. Now, in this chapter, we've also introduced integrals and antiderivatives. And basically, you want to find the antiderivative of this function. This particular one is just going to be 6t cubed over 3 plus t squared over 14 plus a constant. And that is answer, well, this is equal to 2t cubed plus t squared over 14 plus c, which is answer B. Number 16, we need to rewrite it so we can use the power antiderivative rule. So this is equal to the integral of t to the 1/2 power minus t. The fourth root is t to the 1/4 power dt. So now we take the antiderivative of t to the 1/2, which is going to be t to the 1/2 plus 1, which is 3/2, divided by 3/2, minus t to the 1/4 plus 1, which is 5/4, divided by 5/4, plus a constant. So we get 2/3 t to the 3/2 minus 4/5 t to the 5/4 plus constant. And that happens to be answer B. Number 17 is we can rewrite this. Actually, we don't have to rewrite it, but we could write it as 5 times the integral 1 over the square root of 1 minus x squared dx minus 2 integral of 1 over x dx. The antiderivative of 1 over the square root of 1 minus x squared is inverse sine of x. So this is 5 inverse sine of x. The antiderivative of 1 over x is ln of x, so we have minus 2 ln of x. So that is answer D. Now here we're going to be taking antiderivatives also, but it's also called solving a differential equation. An equation that has derivatives in it is called a differential equation. And we're given a differential equation, and they're saying that the graph of y, which is the solution, passes through the point 0 and 5 and has a horizontal tangent there. That means the tangent y prime at 0 is going to be equal to 0 horizontal tangent. So let's start unraveling this problem. The second derivative of y with respect to x, which is also written as y double prime, is 36x. So to calculate y prime, we take the antiderivative. We're going to go backwards. So y prime is equal to 18x squared plus a constant. So we're going to do this twice. We're going to label the first constant C1. And then going all the way to y, we take the antiderivative again, and we get 6x cubed plus C1x plus C2. So this is the solution, and we need to pick C1 and C2 so that the condition that the point 0 and 5 is on the graph, and it has a horizontal tangent line. Well, at x equals 0. So the horizontal tangent line means y prime equals 0 at x equals 0. So plugging in x equals 0, we get 18 times 0 squared plus C1 equals 0. So C1 equals 0 is the first constant. The second constant is that it goes through the point 0 and 6. I'm sorry, 0 and 5. So using the equation for y, we get 5 equals 6 times 0 cubed plus C1, of course, was 0, and then C2. So C2 is equal to 5. So this is 5. C1 was 0. So y equals 6x cubed plus 5 is the answer. Number 19. We want to, if we're given the function x cubed minus 4x, to find the largest open interval where it is decreasing. Let's calculate f prime of x and find the critical points. This is 3x squared minus 4 equals 0. So 3x squared equals 4. X squared equals 4/3. And x squared x equals 2 plus or minus 2 over the square root of 3, which is plus or minus 2 square roots of 3 over 3. So now we need to set up the intervals again. We want to look at minus infinity to minus 2 square roots of 3 over 3. We want to look between minus 2 square roots of 3 over 3 and 2 square roots of 3 over 3. And then finally, 2 square roots of 3 over 3. Oh, let me clean this up a little bit. And infinity. So we need to look at test points. Test points. We pick a point between minus infinity and minus 2 square roots of 3 over 3. If you look at what this value is, we need to pick probably a good number to use is minus 2. That'll be between minus infinity and minus 2 square roots of 3 over 3. And then the easy one to pick for the middle interval is x equals 0. And then for the right interval, picking 2 for the test point. And now we're going to calculate f prime of x at minus 2. So f prime at minus 2, we plug in to here, and we get 3 times 4 minus 4 is more than 0, so it's increasing. We plug in 0, and we get minus 4, which is less than 0, so it's decreasing. And then we plug in 2, and we get 3 times 4 minus 4 is more than 0, so it's increasing. And so the interval where it's decreasing is between minus 2 square roots of 3 over 3 and plus 2 square roots of 3 over 3, which is answer C. Number 20, you don't have to calculate a derivative. You're given the derivative, and you want to find, again, the intervals in which the function is increasing or decreasing. F prime of x equals 0 at x equals 4 and x equals 6. So here again, we want to set up intervals minus infinity to 4, and between 4 and 6, and between 6 and 8, pick our test point. I would pick 3. I would pick 5, and I would pick 7. As long as you pick one point that's in between those points on the end. And now we calculate the derivative of the x. But at x equals 3, plugging in, we get 4 minus 3 times 6 minus 3 is more than 0, so it's increasing. Plug in 5, we get 4 minus 5 times 6 minus 5 is less than 0, so it's decreasing. And plug in 7, and we get 4 minus 7 times 6 minus 7 is more than 0, so it's increasing. So it's increasing on this interval and this interval, and decreasing on the middle interval, and that answer is C, decreasing 4 to 6, and then increasing on the union of minus infinity to 4 and 6 to infinity. Now here we want to graph the rational function given here. You could just about almost do this without even, just by using your head here. Notice you're not going to have any vertical asymptotes because x squared plus 4 is never equal to 0. That takes out this one. That takes out this one. And if you look at the last two functions, this function is an even function, so the only even function is c, because d is an odd function. So the answer is going to be c. But I tell you what, I would pull out my calculator and confirm this. Let's plug in 6 divided by x squared plus 4. And the window, I'm going to zoom to the standard window, and wait a minute, do not want to put in that. Okay, I'm going to zoom to the standard window, and sure enough, we get this graph. We change the y min and y max to 0 and say they have 2 here. It'll look even more like that graph. So there's the function. So the answer is C. Find the extreme values of the function and where they occur. So here, there are no endpoints. But there may be some points where the first derivative is 0, some critical points. So let's calculate the first derivative using the quotient rule, which you remember is x squared minus 1, which is the denominator times the derivative of the numerator, which is 0, minus the numerator times the derivative of the denominator, which is 2x, divided by the denominator squared. So this is equal to minus 2x over x squared minus 1 quantity squared. And that equals 0 at x equals 0. So at x equals 0, it has a horizontal tangent. And what we want to do is look at the points to the left and the right of x equals 0 to see if it's increasing or decreasing. So there are vertical asymptotes. In fact, let's draw the graph of this. If you graph this function at x equals 0, it's minus 1. They're vertical asymptotes at -1 and +1. And if you graph it, you'll see this. And then you'll see this and this. And I would encourage you to graph it. Notice this has to be a local maximum. We can calculate F prime at -1/2, and plugging into the derivative, we get -2 times -1/2 over -1/2 squared -1 quantity squared. That is more than 0, so it's increasing at x equal -1/2. That means it's increasing there, as we can see by the graph. F prime at 1/2 is going to be -2 times 1/2 over 1/2 squared -1 quantity squared. That is less than 0, so it's decreasing. So the answer to this, it has a local maximum at 0 and -1 right here. Number 23, we want to find the absolute maximum minimum values of the following function on the given interval. Now, we're going to first start off by calculating the first derivative of the function. And let's write the function as f of x equal -6x to the -3. The first derivative then is going to be 18. I'm sorry, -6x to the -2. The first derivative is going to be 12 x to the -3 equal 12 over x cubed. And can it be equal to 0? No. So there are no horizontal tangents. So we need to look at the endpoints. Let's look at F 0.5 is equal to -6 over 0.5 squared is equal to -24. And then let's look at F at 2 equal -6 over 4 equal -3/2. So this is the absolute min, and this is the absolute max. So on this page, the absolute maximum value, which is -3/2, occurs at x equals 2. And the absolute minimum value, -24, occurs at x equal 1/2. Then it asks you to graph it. And put it in your calculator you'll quickly see that the graph looks exactly like this. Okay, problem 24, we want to find the absolute maximum and minimum values of the following function over the interval -4 to 3. The first thing we're going to do is calculate the first derivative of the function. It's 2x, and we set it equal to 0, and it's 0 at x equals 0. We then calculate the functional value at 0 to be -9. Now we're going to look at the endpoints. F at -4 is equal to -4 squared -9 is equal to 16 -9 equals 7. So F at -4 equals 7. And then we calculate F at 3 equal 9 -9 equals 0. So looking at these, the maximum occurs at x equal -4, and its value is 7. And the absolute minimum is going to be -9 at 0. So the answer there at x equals 0, the value is -9. And you put this in your calculator, put the function x squared -9 over the intervals involved, and you'll see you get this graph B. Okay, problem 25, we have a driver driving along the highway at 66 feet per second. That's his velocity. Sees an accident ahead and slams on his brakes. What constant acceleration or deceleration is required to stop the car in 242 feet? We'll carry out the following steps here. We'll first write a differential equation that says the acceleration, as you know, is a second derivative of the position with respect to time. And we sometimes write that as S double prime. And since it's going to be a deceleration, we're going to call that the acceleration minus K. And we want to find the value of K, which is the value of deceleration required to stop the car in 242 feet. And so we're going to solve this differential equation. And first of all, we'll take the antiderivative of S double prime, and that would be S prime, and that would be minus KT plus C1. Now the velocity is equal to S prime, first derivative of position, and we're given that S prime is equal to 66 at t equal to 0. So plugging in 0 here, we get minus K times 0 plus C1 equals 66. So C1 is equal to 66. So now we have that S prime is equal to minus KT plus 66. Now let's go ahead and continue to solve this. Take one more antiderivative, and we will get that S is equal to minus kt squared over 2 plus 66t plus C2. Now, we know that at t equals 0, S is equal to 0. So we get 0 equals minus k 0 squared over 2 plus 66 times 0 plus C2. That means that C2 is equal to 0. So now we've solved the differential equation, and S is going to be minus k t squared over 2 plus 66t. And recall C2 is equal to 0. So we can put the first answer in. S is equal to minus k t squared over 2 plus 66t. Now, if we want to find the value of t where the velocity is equal to 0, we solve this and we get minus kt plus 66 equals 0. And this occurs at t equal 66 over k. So at times t equals 66 over k, the velocity is 0. And now we want to lastly find out what value of k is required in order to for the car to have velocity 0 at 242 feet. So we're going to plug in 242 into the position equation for t equals 66 over k and solve for k. So 242 is equal to minus k over 2 times t squared, which is 66 squared over k squared, plus 66 times t, which is 66 over k. And notice we get to cancel out a k here, and we get 242 equals minus 66 squared over 2k plus 66 squared over k. And this equals 66 squared over 2k. And 66 squared over 2k equals 242. And we get, lastly, the equation cross multiplying. We get 484k equals 66 squared, and k equals 66 squared over 484 equals 9. So the value of k, in order for that deceleration to occur fast enough to stop in 242 feet, is k equal 9. And that's problem 25. Number 26, we want to, given the acceleration, initial velocity, the initial position of a body moving along a coordinate line at time t, find the body's position at time t. We're given that the acceleration is equal to 9.8. That means the second derivative of s is equal to 9.8. Going backwards and solving for s prime, which is equal to the velocity, is equal to 9.8 t plus c1. Solving for s, we take the antiderivative of 9.8 t and get 4.9 t squared plus C1t plus C2. Now we know that V at 0 is equal to 3. That means that 9.8 times 0 plus C1 equal to 3. So C1 equals 3. And we know that S at 0 is 7. So that is 4.9 times 0 squared plus 9 times 0 plus C2. So C2 is equal to 7. So the solution for S is S equal 4.9 t squared plus C1 t, which is 3t, plus C2, which is 7. So the answer is B. Number 27, suppose a businessman can sell X gadgets for a price of 250 minus 0.01 X dollars a piece, and it costs the business 1,000 plus 25 X dollars to produce the X gadgets. Determine the production level and the price per gadget required to maximize the profit. Okay, the profit is going to be capital P. It's going to be X times the price, little p of X. And that is going to be X times 250 minus 0.01 X. So the profit is then going to be X times 250 minus 0.01 X minus the cost, which is 1,000 plus 25X. So the profit is 250X minus 0.01 X squared minus 1,000 minus 25X is equal to 225X minus 0.01 X squared minus 1,000. So taking derivative of the profit, we get 225X minus 0.02X equals 0. And we get that X is equal to 225 oh, excuse me, this derivative is 225 here. Derivative of 225X is 225. So solving for X, we get X is equal to 225 divided by 0.02, which is equal to 11,250 gadgets. And the price of 11,250 gadgets, we plug into the price equation, and we get 250 minus 0.01 times 11,250, and we get $137.50. And so the answer is 11,250 gadgets at $137.50. That's price each. And that is the practice test 3.